हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज हम करने जा रहे हैं क्लास 11th यूनिट 7 चैप्टर इक्विलिब्रियम की ऑडियो बुक। सो ये चैप्टर काफ़ी लेंदी हो गया है और ये आज मैं इसका थर्ड पार्ट कर रही हूँ एंड होपफुली ये आज इसका लास्ट डे होगा। इसके बाद मैं इस बुक की पूरी कंपाइल करके आपकी एक ऑडियो बुक बना करके जल्दी ही अपलोड कर दूंगी। थोड़ा वो वीडियो लंबा होगा, अराउंड 8 to 9 आवर्स और मोर देन दैट में बी। चलिए फटाफट करते हैं। बच्चों, आपसे रिक्वेस्ट है कि आप लोग इन ऑडियो बुक्स को ज़्यादा से ज़्यादा अपने दोस्तों के साथ में शेयर करिए ताकि उनको भी इसका बेनिफिट मिल सके, क्योंकि बहुत सारे बच्चों को अभी पता ही नहीं है कि भाई इस तरह की ऑडियो बुक्स भी अवेलेबल हैं जिनसे उनके रिवीजन में इतनी हेल्प मिल सकती है। ये आप सभी लोग अच्छी तरह से समझते हैं, तो अपने दोस्तों की हेल्प करिए, अच्छी बात है। चलिए स्टार्ट करते हैं, टाइम वेस्ट नहीं करते हैं। इसके पहले का हमने सारा ऑडियो बुक में कवर कर लिया है। उनके फर्स्ट और सेकंड पार्ट के मैंने लिंक डिस्क्रिप्शन बॉक्स में दे दिए हैं। अभी मुझे स्टार्ट करना है 7.11 आयनाइजेशन ऑफ एसिड एंड बेसिस से। Arrhenius concept of acid and bases becomes useful in case of ionization of acids and bases, as mostly ionization in chemical and biological system occur in aqueous medium. Strong acids like perchloric acid HClO4, hydrochloric acid HCl, hydrobromic acid HBr, hydroiodic acid HI, nitric acid HNO3 and sulfuric acid H2SO4 are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton donors. Similarly, strong bases like lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide CSOH and barium hydroxide BaOH whole twice are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions OH ion. According to Arrhenius concept, they are strong bases and acids as they are able to completely dissociate and produce H3O ion and OH ions respectively in the medium. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acid and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. Consider the acid-base dissociation equilibrium of a weak acid HA. HA plus H2O gives out H3O positive plus A negative, and H3O positive is a conjugate acid and A negative is a conjugate base, and that is a reversible reaction. In section 7.10.2, we saw that acid or base dissociation equilibrium is dynamic, involving a transfer of proton in forward and reverse directions. Now the question arises that if the equilibrium is dynamic, then with passage of time, which direction is favored? What is the driving force behind it? In order to answer these questions, we shall deal into the issue of comparing the strengths of the two acids or bases involved in the dissociation equilibrium. Consider the two acids HA and H3O positive present in the above mentioned acid dissociation equilibrium. We have to see which among them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as the stronger acid, and the equilibrium will shift in the direction of weaker acid. Say if HA is a stronger acid than H3O positive, then HA will donate protons and not H3O ion, and the solution will mainly contain A negative and H3O ions. The equilibrium moves in the direction of formation of weaker acid and weaker base, because the stronger acid donates a proton to the stronger base. It follows that as a stronger acid dissociates completely in water, the resulting base formed would be very weak. That is, a strong acid have very weak conjugate bases. Strong acids like perchloric acid HClO4, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid will give conjugate base ion ClO4 negative, Cl, Br negative, I negative, NO3 negative and HSO4 negative, which are much weaker bases than H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid, say HA, is only partially dissociated in aqueous medium, and thus the solution mainly contains undissociated HA molecules. Typical weak acids are nitrous acid, hydrofluoric acid and acetic acid. It should be noted that the weak acids have very strong conjugate bases. For example, NH2 negative, O2 negative and H negative are very good proton acceptors and thus much stronger bases than H2O. Certain water-soluble organic compounds like phenolphthalein and bromothymol blue behave as weak acids and exhibit different color in their acids. HIN in and conjugate base ion negative forms. And here you can see this reaction. Such compounds are useful as indicators in acid-base titrations and finding out HIN concentration. 7.11.1 the ionization constant of water and its ionic product. Some substances like water are unique in their ability of acting both as an acid and a base. We have seen this in case of water in section 7.10.2 in presence of an acid. It accepts a proton and acts as the base, while in the presence of a base B negative it acts as an acid by donating a proton. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecule accepts a proton and acts as a base at the same time. The following equilibrium exists: H2O plus H2O. Reversible reaction, it is H3O positive plus OH negative. The dissociation constant is represented by K is equals to H3O positive into OH negative upon H2O. The concentration of water is omitted from the denominator, as water is a pure liquid and its concentration remains constant. H2O is incorporated within the equilibrium constant to give a new constant Kw, which is called the ionic product of water. Kw is equals to H ion into OH ion. The concentration of H positive has been found out experimentally as 1 into 10 to the power minus 7 m at 298 Kelvin. And as dissociation of water produces equal number of H ion and OH ions, the concentration of hydroxyl ions OH negative is equals to H ion is equals to 1 into 10 to the power minus 7 m. Thus, the value of Kw at 298 Kelvin is equals to 1 into 10 to the power minus 4 m square. The value of Kw is temperature dependent as it is an equilibrium constant. The density of pure water is 1000 gram per liter and its molar mass is 18 gram per mole. From this, the molarity of a pure water can be given as, that is 55.55 m. Therefore, the ratio of dissociated water to that of undissociated water can be given as, here you can see the value, that is the 1.8 into 10 to the power minus 9 or approximately 2 in 10 to the power minus 9. Thus, equilibrium lies mainly towards undissociated water. We can distinguish acidic, neutral and basic aqueous solutions by the relative values of the H3O positive and OH negative concentration. Acidic, H3O positive is greater than OH negative. Neutral, H3O positive is equal to OH ion, and basic, H3O positive is less than OH negative. 7.11.2 the pH scale. Hydronium ion concentration in molarity is more conveniently expressed on a logarithmic scale known as the pH scale. The pH of a solution is defined as the negative logarithm to base 10 of the activity of hydrogen ion. In dilute solutions, that is less than 0.01 m, activity of hydrogen ion is equal in magnitude to molarity represented by H ion. It should be noted that activity has no units and is defined as H ion per mole per liter. From the definition of pH, the following can be written here, that pH is equals to minus log H ion. Thus, an acidic solution of HCl will have a pH of 2, and similarly a basic solution of NaOH having OH ion is equals to 10 to the power minus 4 m and H3O ion is equals to 10 to the power minus 10 m will have a pH 10. At 25 degrees Celsius, pure water has a concentration of hydrogen ions. H ion is equals to 10 to the power minus 7 m, hence the pH of pure water is given as pH is equals to 7. Acidic solutions possesses a concentration of hydrogen ions that is greater than 10 to the power minus 7 m, while basic solution possesses a concentration of hydrogen ion that is less than 10 to the power minus 7 m. Thus, we can summarize that acidic solution has pH less than 7, basic has pH greater than 7, and neutral is having pH is equals to 7. Now again consider the equation at 298 Kelvin. Kw is equals to 10 to the power minus 14. Taking negative logarithm on the both side of equation, we obtain here the final equation I am reading, that is equals to minus log 10 to the power minus 14, and pKw is equals to pH plus pOH is equals to 14. Note that although Kw may change with temperature, the variations in pH with temperature are so small that we often ignore it. pKw is a very important quantity for aqueous solutions and controls the relative concentration of hydrogen and hydroxyl ions as their product is a constant. It should be noted that as the pH scale is a logarithmic, a change in pH by just 1 unit also means change in H ion by a factor of 10. Similarly, when the hydrogen ion concentration H ion changes by a factor of 100, the value of pH changes by 2 units. Now you can realize why the change in pH with temperature is often ignored. Measurement of pH of a solution is very essential as its value should be known when dealing with biological and cosmetic application. The pH of a solution can be found roughly with the help of a pH paper that has different color in solutions of different pH. Nowadays, pH paper is available with 4 strips on it. The different strips have different colors at the same pH. The pH in the range of 1 to 14 can be determined with an accuracy of approximately 0.5 using pH paper. Here you can see the figure 7.11. For greater accuracy, pH meters are used. pH meter is a device that measures the pH-dependent electrical potential of the test solution within 0.001 precision. pH meter of the size of a writing pen are now available in the market. The pH of some very common substances are given in table 7.5. See here the table 7.5. The pH of some common substances I am reading because this is important, and name of the fluid and the pH, right? Saturated solution of NaOH, approximate 15, 0.1 m NaOH solution, that is 13, lime water 10.5, milk of magnesia, that is 10, egg white seawater, that is 7.8, human blood 7.4, milk 6.8, human saliva 6.4, black coffee 5, tomato juice approximate 4.2, soft drinks and vinegar approximate 3, lemon juice approximate 2.2, gastric juice approximate 1.2, and 1 m HCl solution that is approximate 0, and concentrated HCl that is approximate minus 1.0. 7.11.3 Ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution. The equilibrium can be expressed by HX plus H2O gives out H3O positive plus X negative. So here you can see all the calculation, and here the C is the initial concentration of the undissociated acid. HX at time t is equals to 0 and alpha is extent up to which HX is ionized into ions. Using these notations, we can derive the equilibrium constant for the above discussed acid dissociation equilibrium. Ka is equals to C square alpha square upon C 1 minus alpha, and that is equals to C alpha square upon 1 minus alpha. Ka is called the dissociation or ionization constant of acid HX. It can be represented alternatively in terms of molar concentration as follows. Ka is equals to H ion S into X negative upon HX. At a given temperature T, Ka is a measure of the strength of the acid HX, that is larger the value of Ka, the stronger is the acid. Ka is dimensionless quantity with the understanding that standard state concentration of all species is 1 m. The values of the ionization constants of some selected weak acids are given in table 7.6. Here I am reading, this is also important because, so here it is hydrofluoric acid 3.5 into 10 to the power minus 4. One side it is acid and another side it is ionization constant Ka, right? Nitrous acid 4.5 into 10 to the power minus 4. Formic acid 1.8 into 10 to the power minus 4. Niacin C5H4NCOOH 1.5 into 10 to the power minus 5. Acetic acid 1.74 into 10 to the power minus 5. Benzoic acid C6H5COOH 6.5 into 10 to the power minus 5. Hypochlorous acid HClO that is 3 into 10 to the power minus 8. Hydrocyanic acid HCN that is 4.9 into 10 to the power minus 10, and phenol is having 1.3 into 10 to the power minus 10. The pH scale for the hydrogen ion concentration has been so useful that besides pKw it has been extended to other species and quantities. Thus we have, so pK is equals to minus log Ka. Knowing the ionization constant Ka of an acid and its initial concentration C, it is possible to calculate the equilibrium concentration of all species and also the degree of ionization of the acid and the pH of the solution. A general stepwise approach can be adopted to evaluate the pH of the weak electrolyte as follows. Step 1. The species present before dissociation are identified as Bronsted-Lowry acids or bases. Step 2. Balanced equations for all possible reaction, that is with the base species acting both as acid as well as base, are written. Step 3. The reaction with the higher Ka is identified as the primary reaction whilst the other is a subsidiary reaction. Step 4. Enlist in a tabular form the following values for each of the species in the primary reaction. A. Initial concentration. C. B. Change in concentration on proceeding to equilibrium in terms of alpha, degree of ionization. C. Equilibrium concentration. Step 5. Substitute equilibrium concentrations into equilibrium constant equation for principal reaction and solve for alpha. Step 6. Calculate the concentration of a species in principal reaction. Step 7. Calculate pH, that is equals to minus log H3O positive ion. The above mentioned methodology has been elucidated in the following examples. 7.11.4 Ionization of weak bases. The ionization of weak base MOH can be represented by equation. MOH gives out M plus OH negative, and in a weak base there is a partial ionization of MOH into M positive and OH negative. The case is similar to that of acid dissociation equilibrium. The equilibrium constant for base ionization is called base ionization constant and is represented by Kb. It can be expressed in terms of concentration and molarity of various species in equilibrium by the following equation. Kb is equals to M positive into OH negative upon MOH. Alternatively, if C is equals to initial concentration of base and alpha is degree of ionization of base, that is the extent to which the base ionizes, when equilibrium is reached, the equilibrium constant can be written as Kb is equals to C alpha square upon C into 1 minus alpha is equals to C alpha square upon 1 minus alpha. The value of the ionization constants of some selected weak bases Kb are given in table 7.7. Here you can see the dimethylamine, that is the base, and its Kb value is 5.4 into 10 to the power minus 4. Triethylamine, its value is having 6.45 into 10 to the power minus 5. Ammonia 1.787 into 10 to the power minus 5. Quinine is a plant product and it is having 1.10 into 10 to the power minus 6. Pyridine C5H5N, it is having the value of Kb 1.77 into 10 to the power minus 9. Aniline C6H5NH2, that value is 4.27 into 10 to the power minus 10. And urea 1.3 into 10 to the power minus 14. Many organic compounds like amines are weak bases. Amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. For example, methylamine, codeine, quinine and nicotine all behaves as very weak bases due to their very small Kb. Ammonia produces OH ion in aqueous solution, NH3 plus H2O reversible and H4 ion plus OH ion. The pH scale for the hydrogen ion concentration has been extended to get pKb is equals to minus log Kb. Now 7.11.5 relation between Ka and Kb. As seen earlier in this chapter, Ka and Kb represent the strength of an acid and a base respectively. In case of a conjugate acid-base pair, they are related in a simpler manner so that if one is known, the other can be deduced. Considering the example of NH4 ion and NH3 we see here, you can see this complete calculation. And here the Ka represents the strength of NH4 ion as an acid and Kb represents the strength of NH3 as a base. It can be seen from the net reaction that the equilibrium constant is equal to the product of equilibrium constant Ka and Kb for the reactions added. Thus Ka into Kb is equals to the final value we will get here, that is 1 into 10 to the power minus 14 m. This can be extended to make a generalization. The equilibrium constant for a net reaction obtained after adding two or more reactions equal the product of the equilibrium constant for individual reactions. So K net is equals to K1 into K2 into so and so on. Similarly, in case of a conjugate acid and base pair, Ka into Kb is equals to Kw. Knowing one the other can be obtained, it should be noted that a strong acid will have a weak conjugate base and vice versa. Alternatively, the above expression Kw is equals to Ka into Kb can also be obtained by considering the base dissociation equilibrium reaction. Here you can see this reaction and the value of Kb is BH positive into OH negative upon B. As the concentration of water remains constant, it has been omitted from the denominator and incorporated within the dissociation constant. Then multiplying and dividing the above expression by H ion, we get Kb is equals to BH positive OH negative, H positive upon B into H positive. And that is the final value Kw upon Ka. So Ka into Kb is equals to Kw. It may be noted that if we take negative logarithm of both sides of the equation, then pK values of the conjugate acid and base are related to each other by this equation. pKa plus pKb is equals to pKw is equals to 14 and at 298 Kelvin. 7.11.6 Di and polybasic acid and di and polyacidic bases. Some of the acids like oxalic acid, sulfuric acid and phosphoric acids have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic or polyprotic acids. The ionization reaction, for example, for a dibasic acid H2X are represented by the equation H2X gives out H ion plus HX negative and HS negative is giving H ion plus X2 negative. And the corresponding equilibrium constant are given below. Ka1 is equals to H ion into Hx negative upon H2x. And the next Ka2 value is the H positive into X2 negative upon Hx negative. Here Ka1 and Ka2 are called the first and second ionization constant respectively of the acid H2X. Similarly, for the tribasic acid H3PO4, we have three ionization constants. The values of the ionization constants for some common polyprotic acids are given in table 7.8. Here you can see. It can be seen that higher order ionization constant are smaller than the lower order ionization constant of a polyprotic acid. The reason for this is that it is more difficult to remove a positively charged proton from a negative ion due to electrostatic forces. This can be seen in the case of removing a proton from the uncharged H2CO3 as compared from a negatively charged HCO3 negative. Similarly, it is more difficult to remove a proton from a doubly charged HPO42 negative ion as compared to H2PO4 negative. Polyprotic acid solutions contain a mixture of acids like H2A, HA negative and A2 negative in case of a diprotic acid. H2A being a strong acid, the primary reaction involves the dissociation of H2A and H3O positive in the solution comes mainly from the first dissociation step. 7.11.7 Factors affecting the acid strengths. Having discussed quantitatively the strengths of acid and bases, we come to a stage where we can calculate the pH of a given acid solution. But the curiosity rises about why should some acids be stronger than others? What factors are responsible for making them stronger? The answer lies in its being a complex phenomena. But broadly speaking, we can say that the extent of dissociation of an acid depends on the strength and polarity of HA bond. In general, when the strength of HA bond decreases, that is the energy required to break the bond decreases, HA becomes a stronger acid. Also, when the HA bond becomes more polar, that is the electronegativity difference between the atoms H and A increases and there is a marked charges separation, cleavage of the bond becomes easier, thereby increasing the acidity. But it should be noted that while comparing elements in the same group of the periodic table, HA bond strength is a more important factor in determining acidity than its polar nature. As the size of A increases down the group, HA bond strength decreases and so the acid strength increases. For example, size increases, HF is very less than HCl is very less than HBr is very less than HI. Acid strength, it means it is increasing as the size is increasing. Similarly, H2S is a stronger acid than H2O. But when we discuss elements in the same row of the periodic table, HA bond polarity becomes the deciding factor for determining the acid strength. As the electronegativity of A increases, the strength of the acid is also increases. For example, electronegativity of A increases, CH4 is less than NH3 is less than H2O is less than HF. That means electronegativity is increasing as the acid strength increases. 7.11.8 Common ion effect in the ionization of acid and bases. Consider an example of acetic acid dissociation equilibrium represented as CH3COH gives out H ion plus CH3CO negative. Here you can see the value of Ka, H ion into acetate ion that is AC negative upon HAC. Addition of acetate ions to an acetic acid solution results in decreasing the concentration of hydrogen ions. Also, if H ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid. that is in a direction of reducing the concentration of hydrogen ions. This phenomena is an example of common ion effect. It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species is already present in the dissociation equilibrium. Thus, we can say that common ion effect is a phenomena based on the Le-Chatelier's principle discussed in section 7.8. In order to evaluate the pH of the solution resulting on addition of 0.05 m acetate ion to a 0.05 m acetic acid solution, we shall consider the acetic acid dissociation equilibrium once again. Here you can see the complete calculation. 7.11.9 Hydrolysis of salts and the pH of their solution. Salts formed by the reaction between acids and bases in definite proportions undergo ionization in water. The cations and anions formed on ionization of salts either exist as hydrated ions in aqueous solutions or interact with water to reform corresponding acid or bases depending upon the nature of salts. The later process of interaction between water and cation anions or both of the salt is called hydrolysis. The pH of the solution gets affected by the interaction. The cations, that is example sodium ion, potassium ion, calcium ion, barium ion, etc., of strong bases and anions like chloride, bromide, NO3 negative, ClO4 negative, etc., of strong acids simply get hydrated but do not hydrolyze, and therefore the solution of salts formed from strong acids and bases are neutral, that is their pH is 7. However, the other category of salts do undergo hydrolysis. We now consider the hydrolysis of the salts of the following types. Number 1. Salts of weak acid and strong base, example CH3COONA. Number 2. Salts of strong acid and weak base, that is NH4Cl. And number 3. Salts of weak acid and weak base, that is CH3CONH4. In the first case, CH3COONA being a salt of weak acid and CH3COOH and a strong base, NaOH gets completely ionized in aqueous solution. Here you can see the reaction. Acetate ion thus formed undergoes hydrolysis in water to give acetic acid and OH ions. You can see this reaction. Acetic acid being a weak acid, that Ka is equals to 1.8 into 10 to the power minus 5, remains mainly unionized in solution. This results in increase of OH ion concentration in solution, making it alkaline. The pH of such a solution is more than 7. Similarly, NH4Cl formed from weak base NH4OH and strong acid, HCl in water dissociates completely. NH4Cl gives out NH4 ion plus Cl negative. Ammonium ions undergo hydrolysis with water to form NH4OH and H ion. And here you can see this reaction. Ammonium hydroxide is a weak base. Kb is equals to 1.77 into 10 to the power minus 5 and therefore remains almost unionized in solution. This results in increased of H ion concentration in solution, making the solution acidic. Thus, the pH of NH4Cl solution in water is less than 7. Consider the hydrolysis of CH3COONH4 salt formed from weak acid and weak base. The ions formed undergo hydrolysis as follow. CH3CO negative plus NH4 ion plus H2O, reversible reaction it is, and it is forming CH3COOH plus NH4OH. And here you can see CH3COH and NH4OH also remain into partially dissociated form, and you can see all the dissociated form. Without going into detailed calculation, it can be said that degree of hydrolysis is independent of concentration of solution and pH of solution is determined by their pK values. pH is equals to 7 plus 1 by 2 pKa minus pKb. The pH solution can be greater than 7 if the difference is positive and it will be less than 7 if the difference is negative. 7.12 Buffer solutions. Many body fluids, example blood or urine, have definite pH and any deviation in their pH indicates malfunctioning of the body. The control of pH is also very important in many chemical and biochemical processes. Many medical and cosmetic formulation require that these be kept and administered at a particular pH. The solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali are called buffer solutions. Buffer solution of known pH can be prepared from the knowledge of pKa of the acid or pKb of base and by controlling the ratio of the salt and acid or salt and base. A mixture of acetic acid and sodium acetate acts as buffer solution around pH 4.75 and a mixture of ammonium chloride and ammonium hydroxide acts as a buffer around pH 9.25. You will learn more about buffer solution in higher classes. 7.12.1 Designing Buffer Solutions. Knowledge of pKa, pKb and equilibrium constant help us to prepare the buffer solution of known pH. Let us see how we can do this. Preparation of acidic buffer. To prepare a buffer of acidic pH, we use weak acid and its salt formed with a strong base. We develop the equation relating the pH, the equilibrium constant Ka of weak acid and ratio of concentration of weak acid and its conjugate base. For the general case where the weak acid Ha ionizes in water, you can see this calculation here. The expression 7.40 is known as Henderson-Hasselbalch equation, and the quantity A negative upon Ha is the ratio of concentration of conjugate base anion, that is of the acid, and the acid present in the mixture. Since acid is a weak acid, it ionizes to a very little extent and concentration of Ha is negligibly different from concentration of acid taken to form buffer. Also, most of the conjugate base A negative comes from the ionization of salt of the acid. Therefore, the concentration of conjugate base will be negligibly different from the concentration of salt. Thus, equation 7.40 takes from the pH is equals to pKa plus log salt upon acid. In the equation 7.39, if the concentration of A negative is equal to the concentration of Ha, then pH is equals to pKa because value of log 1 is 0. Thus, if we take molar concentration of acid and salt same, the pH of the buffer solution will be equal to the pKa of the acid. So for preparing the buffer solution of the required pH, we select that acid whose pKa is close to the required pH. For acetic acid, pKa value is 4.76. Therefore, pH of the buffer solution formed by acetic acid and sodium acetate taken in equal molar concentration will be around 4.76. A similar analysis of a buffer made with a weak base and its conjugate acid leads to the result POH is equals to pKb plus log conjugate acid BH positive, that is, and base upon base B. And pH of a buffer solution can be calculated by using the equation pH plus POH is equals to 14. We know that pH plus POH is equals to pKw and pKa plus pKb is equals to pKw. On putting these values in the equation, it takes the form as follows. Here we will get this equation pH is equals to pKa plus log conjugate acid BH positive upon base B. If molar concentration of base and its conjugate acid cation is same, then pH of the buffer solution will be same as pKa for the base. pKa value for ammonia is 9.25. Therefore, a buffer of a pH close to 9.25 can be obtained by taking ammonia solution and ammonium chloride solution of same molar concentration. For a buffer solution formed by ammonium chloride and ammonium hydroxide, equation becomes pH is equals to 9.25 plus log conjugate acid upon base, and that is BH positive upon B. pH of a buffer solution is not affected by dilution because ratio under the logarithmic term remains unchanged. 7.13 Solubility Equilibria of sparingly soluble salt. We have already known that the solubility of ionic solids in water varies a great deal. Some of these, like calcium chloride, are so soluble that they are hygroscopic in nature and even absorb water vapor from atmosphere. Others, such as lithium fluoride, have so little solubility that they are commonly termed as insoluble. The solubility depends on a number of factors, important amongst which are the lattice enthalpy of the salt and the solvation enthalpy of the ions in a solution. For a salt to dissolve in a solvent, the strong forces of attraction between its ion lattice enthalpy must be overcome by the non-ion-solvent interaction. The solvation enthalpy of ions is referred to in terms of solvation, which is always negative, that is, energy is released in the process of solvation. The amount of solvation enthalpy depends on the nature of the solvent. In case of a nonpolar covalent solvent, solvation enthalpy is small and hence not sufficient to overcome lattice enthalpy of the salt. Consequently, the salt does not dissolve in nonpolar solvent. As a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy, so that later may be overcome by former. Each salt has its characteristic solubility which depends on temperature. We classify salts on the basis of their solubility in the following three categories. Category 1, Category 2, Category 3, and soluble, slightly soluble, and sparingly soluble. And here in the case of soluble, the solubility is greater than 0.1 m. In slightly soluble, that is the 0.01 m is less than solubility is less than 0.1 m, and in the sparingly soluble, that is the solubility is less than 0.01 m. We shall now consider the equilibrium between the sparingly soluble ionic salt and its saturated aqueous solution. 7.13.1 Solubility product constant. Let us now have a solid like barium sulfate in contact with its saturated aqueous solution. The equilibrium between the undissolved solid and the ions in a saturated solution can be represented by the equation BaSO4 gives out Ba2 positive plus SO4 2 negative, and the equilibrium constant is given by the equation K is equals to Ba2 positive SO4 2 negative upon BaSO4. For a pure solid substance, the concentration remains constant, and we can write Ksp is equals to KBaSO4 is equals to Ba2 positive BaSO4 2 negative. We call Ksp the solubility product constant or simply solubility product. The experimental value of Ksp is above equation at 298 K is 1.1 into 10 to the power minus 10. This means that for solid barium sulfate in equilibrium, when its saturated solution, the product of the concentrations of barium and sulfate ion is equal to its solubility product constant. The concentration of the two ions will be equal the molar solubility of the barium sulfate. If molar solubility is S, then 1.1 into 10 to the power minus 10, and S is equals to S square, and the value of S is then 1.05 into 10 to the power minus 5. Thus, molar solubility of a barium sulfate will be equal to 1.05 into 10 to the power minus 5. A salt may given on dissociation two or more than two anions and cations carrying different charges. For example, consider a salt like zirconium phosphate of molecular formula Zr 4 positive the whole 3 and PO4 3 negative the whole 4. It dissociates into 3 zirconium cations of charge plus 4 and 4 phosphate ions of charge minus 3. If the molar solubility of zirconium phosphate is S, then it can be seen from the stoichiometry of the compound that here you can see the calculation. A solid salt of the general formula MXP positive XYQ negative with molar solubility S in equilibrium with its saturated solution may be represented by the equation MX XY is the reversible reaction XMP positive plus YXQ negative, and its solubility product constant is given by, here you can see this. The term Ksp in equation is given by Qsp when the concentration of one or more species is not concentration under equilibrium. Obviously, under equilibrium conditions, Ksp is equals to Qsp, but otherwise it gives the direction of the process of precipitation or dissolution. The solubility product constants of a number of common salts at 298 K are given in table 7.9. Here you can see the table 7.9, the solubility product constants, Ksp of some common ionic salts at 298 K. 7.13.2 common ion effect on solubility of ionic salts. It is expected from Le-Chatelier's principle that if we increase the concentration of any one of the ions, it should be combined with the ion of its opposite charge and some of the salt will be precipitated till once again Ksp is equals to Qsp. Similarly, if the concentration of one of the ions is decreased, more salt will dissolve to increase the concentration of both the ions till once again Ksp is equals to Qsp. This is applicable even to soluble salts like sodium chloride, except that due to higher concentration of the ions, we use their activities instead of their molarities in the expression for Qsp. Thus, if we take a saturated solution of sodium chloride and pass HCl gas through it, then sodium chloride is precipitated due to increased concentration of chloride ion available from the dissociation of HCl. Sodium chloride thus obtained is very high purity and we can get rid of impurities like sodium and magnesium sulfates. The common ion effect is also used for almost complete precipitation of a particular ion as it's a sparingly soluble salt with very low value of solubility product for gravimetric estimation. Thus, we can precipitate silver ion as silver chloride, ferric ion as its hydroxide or hydrated ferric oxide, and barium ion as its sulfate for quantitative estimations. The solubility of salts of weak acids like phosphates increase at lower pH. This is because at lower pH, the concentration of the anion decreases due to its protonation. This in turn increases the solubility of the salt as that Ksp is equals to Qsp. We have to satisfy two equilibria simultaneously. You can see this complete calculation here. Thus, solubility S increases with increase in H ion or decrease in pH. Summary. When the number of molecules leaving the liquid to vapor equals the number of molecules returning to the liquid from vapor, equilibrium is said to be attained and is dynamic in nature. Equilibrium can be established for both physical and chemical processes, and this stage rate of forward and reverse reaction are equal. Equilibrium constant Kc is expressed as the concentration of products divided by reactants, each term raised to the stoichiometric coefficient. For reaction AA plus BB reversible CC plus DD, Kc is equals to C to the power C D to the power D upon A to the power A and B to the power B. Equilibrium constant has constant value at a fixed temperature, and this stage all the macroscopic properties such as concentration, pressure, etc. become constant. For a gaseous reaction, equilibrium constant is expressed as Kp and is written by replacing concentration terms by partial pressure in Kc expression. The direction of reaction can be predicted by reaction quotient Qc, which is equal to Kc at equilibrium. Le-Chatelier's principle states that the change in any factor such as temperature, pressure, concentration, etc. will cause the equilibrium to shift in such a direction so as to reduce or counteract the effect of the change. It can be used to study the effect of various factors such as temperature, concentration, pressure, catalyst and inert gases on the direction of equilibrium, and to control the yield of products by controlling these factors. Catalyst does not affect the equilibrium composition of reaction mixture but increases the rate of chemical reaction by making available a new lower energy pathway for conversion of reactants to products and vice versa. All substances that conduct electricity in aqueous solution are called electrolytes. Acid, bases and salts are electrolytes, and the conduction of electricity by their aqueous solution is due to anions and cations produced by the dissociation or ionization of electrolytes in aqueous solution. The strong electrolytes are completely dissociated. In weak electrolyte, there is equilibrium between the ions and the unionized electrolyte molecules. According to the Arrhenius acid give hydrogen ions while base produces hydroxyl ion in their aqueous solution. Bronsted-Lowry, on other hand, defined an acid as a proton donor and a base as a proton acceptor. When a Bronsted-Lowry acid reacts with a base, it produces its conjugate base and a conjugate acid corresponding to the base with which it reacts. Thus, the conjugate pair of acid-base differs only by one proton. Lewis further generalized the definition of an acid as an electron pair acceptor and a base as an electron pair donor. The expressions of ionization constant of weak acid and weak bases are developed using Arrhenius definition. The degree of ionization and its dependence on concentration and common ion are discussed. The pH scale for the hydrogen ion concentration has been introduced and extended to other quantities. pK is equals to minus log Ka, pKb is equals to minus log Kb, and pKw is equals to minus log Kw, etc. The ionization of water has been considered, and we note that equation pH plus pOH is equals to pKw is always satisfied. The salts of strong acid and weak base, weak acid and a strong base, and weak acid and weak base undergo hydrolysis in aqueous solution. The definition of buffer solutions and their importance are discussed briefly. The solubility equilibrium of sparingly soluble salts is discussed, and the equilibrium constant is introduced as solubility product constant, that is KSP. Its relationship with solubility of the salt is established. The conditions of precipitation of the salt from their solutions or their dissolution in water are worked out. The role of common ion and the solubility of sparingly soluble salts is also discussed. Chapter done. So students, if these audiobooks are helping you, then press the like button. And if you are new in my channel, then please subscribe and share with your friends also, so that they will also get the benefit of these audiobooks. So take care everyone. See you soon in my next video. Till then, just stay tuned with me. Bye-bye.